So yesterday we looked at y equals x squared. And we saw that that basic function that we had some points that were always the same that we could transform into other things. We could shift them left, right, up, down, and reflect them over. Turns out you can do the same thing with anything you have a parent function of, that you know what it looks like and some of its basic points. Because we know those points all move in the same direction, the same number of units. So y equals x squared, we have our 5 points from yesterday that we were moving around. We're going to introduce 4 new parent functions to do the same thing with. So y equals x cubed. There's our x-axis and our y-axis. And so the points we're going to use are 0, 0, 1, 1, negative 1, negative 1, two, 8, and negative 2, negative 8. Zero cubed is 0, 1 cubed is 1, 2 cubed is 8, negative 1 cubed is negative 1, negative 2 cubed is negative 8. So those are the 5 points. Lots of times when you shift things around, 2, 8 or negative 2, negative 8 shift off of the axis that you're going to be on. So that's not a big deal. The big 3 here that you got to make sure that you're shifting correctly are negative 1, 0, 0, and 1, 1. Y equals the square root of x, which undoes x squared. Square roots and squareds being related like that. It has 3 points that we use. 0, 0, 1, 1, and 4, 2. So in x cubed, I made the xy table form. Here in the square root of x, I'm putting that table form in point form. The xy tables and the points are directly connected. So those are the 3 points you're going to shift around for anytime you can recognize that you have the square root of x as your parent function. The cube root of x is tied to x cubed in the same way that the square root of x is tied to x squared. And so the points that we're going to use are 0, 0, cube root of 1 is 1. Cube root of 8 is 2. Cube root of negative 1 is negative 1. Cube root of negative 8 is negative 2. There's our xy table. So those are the points we use. 0, 0, 1, 1, 8, 2, negative 1, negative 1, and negative 8, negative 2. And again, when we're shifting around here, negative 8, negative 2, or 8, 2 often get shifted off of the graph. And so the important ones to make sure that we are shifting around correctly are, of course, those middle 3. Notice those middle 3 are the same middle 3 as y equals x cubed, which is why when I started, I said you have to know both the shape and the points. If you're using those same 3 points, but you're using the x cubeds where you have a cube root, you're wrong in your graph. And so you have to couple the shape and the points together. What does the cube root of x look like versus what does x cubed look like? And the last one we're going to do is the absolute value of x. So we have 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. Absolute values make positives into negatives, and so we have a V. And 0, 0, 1, 1, 2, 2. Let's do points this time. So we have some in point form and some in XY table form. The absolute value takes our negatives and makes them positive. So those are our 5 basic shapes that we're going to move around. The one from yesterday, y equals x squared, and our 4 new ones, y equals x cubed, y equals the square root of x, y equals the cube root of x, and y equals the absolute value of x. We're going to be doing the same things we did yesterday, shifting them horizontally, shifting them vertically, reflecting them. So remember that those horizontal shifts are, that's where we're moving every point horizontally, left or right. And so yesterday we saw this with our parabolas. We would move the points however far our horizontal shift was. So that we would then get our transformed parabola. Only difference today is that we're going to be doing them with our other shapes. And so you're going to be taking those new points that you know looking at our new functions, and you're going to be shifting them horizontally. And then drawing in your new appropriate shape. So no, not a big deal here. We're still doing the same thing. We just now have to identify which one of those basic functions we're in. Vertical shifts are the same thing. We're going to be translating every point of the parent function vertically, up or down. So yesterday we did this with our parabolas. We took our basic parabolas and we shifted them up or down. Every point got moved to the same distance, and we knew the basic shape was a parabola the whole time. So today we have to take our other basic shapes, and we're going to be doing the same thing, shifting them up or down. And then drawing in our new same shapes. Last one is our reflections. So we did mirror images over the x-axis for our reflections. The y's became negative y's. We flipped it down. That was from yesterday. So we're going to be doing the same types of things here, except we have to identify the correct shape and use that shape's points and flip those points down. Alright, so let's go look at these. Where do these shapes come from? When we look at square roots, if we're trying to graph y equals the square root of x plus 3, all minus 2, we see the square root. So we know our basic shape is going to start with a square root. So it should start by looking like the basic shape 0, 0, 1, 1, 4, 2. That's the basic shape we're shifting around. So that's our parent function, y equals the square root of x. So if we plug in negative 3, we're going to have the square root. Oh, changing the x to negative 3, plus 3, minus 2. Negative 3 plus 3 is 0. Square root of 0 is 0. 0 minus 2 is negative 2. So we get the point, negative 3, negative 2. If we plug in negative 2, negative 2 plus 3 minus 2, we get 1 minus 2. Square root of 1 is 1. 1 minus 2 is negative 1. And what happens if we plug in -1? So -1 plus 3 minus 2. What's the square root of 2? Ooh, the square root of 2 is a decimal? Awesome. Not only is it a decimal, it's an irrational number. It's a decimal that goes on forever without repeating. So we get a terrible decimal. Where are we going to put that terrible decimal on our picture? I'm not. Why would I try to put the square root of 2 minus 2, some terrible decimal, onto my graph? I want to be graphing good points, not bad points. Oops, put that in the wrong place. Square root of 2 minus 2. Forgot to put in the -1 up here. So what about when we plug in 0? We'll have 0 plus 3. Square root of 3 minus 2. Again, some terrible decimal that I'm not going to want to graph. But what happens when we plug in 1? We get the square root of 1 plus 3 minus 2. Square root of 4 minus 2. 2 minus 2, which is 0. And there's our next good point. 1, 0. We know the basic shape is going to look like that. So what happened to our parent function? 0, 0, 1, 1, 4, 2. We shifted it just like before, doing the opposite of what we saw inside. Horizontally, we're shifting -3. Vertically, we're shifting the same as what we see, -2. Let's see if that works. If we take the point 0, 0 and we shift it left 3 and down 2. 1, 2, 3, 1, 2. Oh, hey, look at that. If we take the point 1, 1 and we shift it 1, 2, 3, 1, 2. If we take the point 4, 2 and we shift it 1, 2, 3, 1, 2. I get the 3 points I got by making the table. Which one is easier to do? Most people think the shifting method is a far easier method of graphing. Did we reflect it? No. And now we get the really cool questions of domain and range. Domain being all the x's that we can put in. Well, where do our x's start? So our x's start here, right? That's -3. There are no x's smaller than that are producing points on the graph. But we got points all through here. And so our domain is from 3 to infinity. Wacky. In square roots, you have a domain that's not all real numbers. We can't put in -4 because we can't take the square root of a negative number. It's not a real number. It's an imaginary number. So we got to be careful when we're stating our domain to only state the x's that we can actually plug into the square root. Our range here. Our range starts down here. And we're going up and up and up. We'll keep on going up. We don't just stop over here. We keep going up and we keep going up and we keep going up. It might take us a really long time to get high on the y-axis, but some x is going to produce that y. And so our range goes from -2 all the way to infinity. Let's look at the next one. So we have the square root of x plus 5, and so we are looking at the same parent function, y equals the square root of x. We are shifting those x points the opposite of what we see inside, minus 5, and the same as what we see outside. The y is going up plus 5. This negative is telling us that yes, we're going to reflect it over the x-axis. And so we're going to take our original points, 0, 0, 1, 1, and 4, 2. We're going to reflect them over the axis. So we're going to get, I'm going to use green, 0, 0, 1, negative 1, 4, negative 2. And then we're going to shift those points left 5 and up 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. Shifting the other points, left 5 and up 5. And drawing in my shape. The domain. Let's see, our x's start here. Let's use a different color for that. So our x's start here, which is negative 5, and continue that way. So negative 5 to infinity. Our y start here at positive 5, and this time continue down this way, and so we're at positive 5 to infinity. So the hard part here for a lot of students is identifying what the basic shape is. You got to look at what you're trying to graph and pick out the important piece. That cube this time is telling us that the parent function is going to be y equals x cubed. So we are shifting right 1, the opposite of what we see inside, and up 4, the same as what we see outside. We don't have a negative in front, so we're not reflecting this time. So our parent function, y equals x cubed, you're probably going to have to look these points up until you know what they are. I have them memorized because I used them enough. So there's our basic shape. That's our parent function. We're going to shift that right 1 and up 4. So move it right 1 and up 4. And here's what I talked about earlier about lots of times one of the 2 points gets shifted right off of the page. This point, when we shift it over 1 and up 4, 1, 2, 3, 4, is off our page. So we just don't put it in anymore. Our domain, all real numbers. Our range. What y's come out of here? Well, all the positive y's come out because we can put all the positive x's in, and all the negative y's come out because when you cube a negative times a negative times a negative is still a negative. So our range is also all real numbers. When we say that in interval notation, that is negative infinity to positive infinity. Negative infinity to positive infinity. We've done a lot with square roots, but there are other roots we can take. We're going to look at the cube root because that's the graph that we're taking. So cube roots and square roots and all roots are connected by thinking about what it's taking the inverse of. What's its undoing? So cube roots undo cubes. So some cubes that we should know are 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, What's 4 cubed? 64. What's 5 cubed? What's 5 cubed? 125. Cube roots undo those. So the cubed root, which we write with a little 3 inside the root symbol, is 2. The cubed root of 27 is 3. It's telling you, look for what number is cubed underneath here. So 3 cubed is 27. The cubed root and the cubed are going to cancel each other out. I'm going to put a negative 64 under there. Negatives aren't a big deal because it's a cubed root. A negative times a negative times a negative is a negative. So the cubed root of negative 64 is just 4. So that's how we find the cube root of a number. You look for what cubed is that number. In Algebra 2, you're going to learn how to break down cubes and fourths and fifths and any root you want, a lot like we're doing with square roots when we're reducing radicals when you look at those notes this weekend. So know that those notes get extended for other types of roots that you take, so you definitely want to be thinking and working hard on getting that reducing radicals part down. So then graphing the cube roots is going to be no big deal. We see the cubed root, so we know our parent function is the cube root of x. We're shifting the opposite of what we see inside. So our x's, we're moving to the left 5. Our y's are the same as what's on the outside. We're moving down 2. So we know what our parent function looks like. Oh shoot, I've been doing those in red. We are not reflecting it because there's no negative in front. So we're just going to shift it. Down 5. Wait, sorry, not down. Right, left. Left 5, down 2. So we're taking each one of the points, moving them left 5 and down 2. Which takes this one left off the thing. So we're not going to worry about that one. Whoa, sorry about that. 1, 2, 3, 4, 5, 6, 7. And you sketch back in your shape. Domain of a cube root, all real numbers. You can put in any x you want. It's not going to blow up a cube root. And range, you're going to get all the y's out. Any number can come out of this if you put in a large enough number for x. So that is graphing using parent functions. Try the homeworks, check the homeworks, and see how you do.